Yeah, so thank you for organizing this, despite the fact that we can't meet in person, obviously. Really excited to give this talk again. And if you listen to the North Central GSA conference or the Ore Deposit Hub, the first early career session back in May, you've heard this talk before, so the slides will look familiar. And the topic of my talk today is dacitic melts and sulfide and sulfate saturation. So we're going to step away from the mafic and ultramafic compositions that we've heard about all morning and take a break and go a little bit to the more intermediate to evolved melts. So why do we care about sulfur in more evolved melts? They obviously don't have the same magmatic sulfide deposits that are very well known throughout the world. But the two main reasons are kind of shown on this screen. So in 1991, Mount Pinatubo erupted in the Philippines, and it was a dacitic volcanic system, and it released 10 million tons of sulfur over the course of a few days, which is a huge amount of sulfur that was really difficult and still is really difficult to reconcile with the dacitic magma that erupted along with it. And so that kind of coined the term at the excess sulfur problem in these more evolved magmatic systems. And so geologists have gone through a lot of trouble to try to reconcile this huge amount of sulfur released in the vapor phase with the amount of sulfur that can be dissolved back into these more evolved melts. And second, so Bingham Canyon is shown on the right. That's one of the world's largest porphyry copper deposits. And so these porphyry copper deposits are copper sulfide mainly deposits that are related to more intermediate to evolved magmatic systems. And this system, again, is estimated to have had about 1 billion tons of sulfur go through this system. And so that is also a huge amount of sulfur. And so these are two main reasons that sulfur does still matter in these more evolved systems. And that's the kind of the point of my talk today. And just as a quick refresher, so we have basically three main components of a magma. And today, the focus of the talk is the silicate melt portion. And so when we think about what controls sulfur in silicate melts, because sulfur is a heterovalent element and its behavior really is dictated by the oxidation state of the system, which in turn dictates the main oxidation state of the sulfur. Determining the oxidation state of the system is is an important variable to understand. And so in the diagram on the right, we have the four main oxidation states of sulfur found in magmatic systems, and the sulfate and sulfide are the dominant forms. So under reduced conditions, the sulfide is the dominant oxidation state, as we probably well know. And as you get progressively more oxidized, the sulfate oxidation state becomes the dominant one in systems. And this variable that we use to describe this is FO2, and it's the oxygen fugacity. And it's basically a partial pressure of oxygen in the system. And I'm going to define the FO2 today using mineral redox buffers, which are really common to use in geology. There's many different buffers that we can reference. But today we're going to use the FMQ mineral redox buffer, which is the reaction of phayolite plus oxygen to produce magnetite and quartz. And through decades of research into sulfur in silicate melts, two of the main variables that we now know really dictate the behavior of sulfur and how much sulfur you can stuff into a silicate melt are one, oxidation state, as I just mentioned. So sulfate is much more soluble in silicate melts than sulfide. And number two, composition. A mafic magma can dissolve an order of magnitude more sulfur than a felsic magma. And so from these two box diagrams here, you can see that an oxidized mafic magma can hold the most amount of sulfur, and a reduced felsic magma would hold the least amount, to be able to dissolve the least amount of sulfur. And just one final intro slide here. When we're talking about reduced versus oxidized systems, two main parameters that we like to define are the sulfur content at sulfide saturation, SCSS, and that's the maximum amount of sulfur that a melt can dissolve before it saturates with an iron sulfide liquid. And conversely, in oxidized systems, we talk about the SCAS, which is the sulfur content at anhydrite saturation. And of course, anhydrite is a calcium sulfate mineral, and the SCAS describes the maximum amount of sulfate that a melt can dissolve before saturating with sulfate. And it's important to note that in these previous studies, since the pioneering work of Fincham and Richardson in 1954, that most of the studies focus on either the SCSS or the SCAS. And that's assuming that in the first case, that most of the sulfur is present as sulfide, and in the latter case, most of the sulfur is present as sulfate. And as we might guess, a lot of studies have focused on mafic systems because those are really, they're spectacular with their sulfide mineralization and generally easier to work with, I think, and see examples of in the field. But an important question is what happens kind of at intermediate FO2 values or between the SCSS and SCAS. And there's really been only one model that links the SCSS and SCAS. And it's basically a model for the maximum amount of sulfur that a melt can dissolve as a function of the FO2 or oxygen fugacity. And this work was done, it was based on experiments done by Pedro Hugo in 2005, where he looked at sulfide and sulfate saturation in mafic basaltic silicate melts. And he performed these experiments at in a range of FO2. And so on this diagram, I have the FO2 on the x-axis, and this delta FMQ is log units relative to the phthalate magnetite quartz mineral redox buffer, so that mineral equilibria is at 0, and as you go progressively to positive values, you're getting more oxidized, and on the other side, if you go to the more negative values, you're getting progressively more reduced. And so on this left side of the diagram, we're talking about SCSS, and on the right side, we're talking about SCAS. And on the y-axis is the measured sulfur content of the basaltic melt from those experiments. So here are the experiments. He did them at different FO2, and like we saw before, a more oxidized melt can dissolve more sulfur than a more reduced melt. And this black line is the result of the model that they came up with, and that was presented in 2009 and 2010. And this is from the 2009 paper. And really what you can see is this great increase in the maximum sulfur that can be dissolved in the melt with FO2 at this intermediate range. And when you get to this, you kind of reach this maximum value, and then you slightly decrease again to go back to the SCAS. So there is this maximum sulfur in the melt value that is represented by this vertical line, and that's what the model predicts. And so that the experiments were, this model is based on experiments in a mafic composition. And when they applied this same model to the dacite composition, that's from the experiments from Karen Rutherford in 1985 and 87, the model you can see does fairly well, given the kind of limited data points that were available, but there is a lot of spread there's a lot of uncertainty in the measurements, and there's noticeably a big gap kind of in this intermediate range. And so the main question that these experiments were aiming to resolve is to rigorously test this, I'm going to call this the Hugo's SCSS and SCAS model, on an evolved silicate melt. In particular, we're going to use a dacite melt, just like the experiments from Carol and Rutherford. And this is really important to do because in contrast to the more primitive magmas, which are generally thought to be more reduced, closer to FMQ, these more evolved arc magmas in particular are thought to be more oxidized, generally in this FMQ +1 to even +3 region. And this is really important because this is where the sulfide-sulfate transition occurs. And so these processes are probably really affecting these more evolved magmas. So to do this, I conducted 6 experiments at 6 different FO2 values. And the main point of these experiments was to use a natural dacite composition at kind of mid to upper crustal temperature pressure conditions and to vary the FO2 of the system. So here are the 6 FO2 values that I used relative to the FMQ buffer. So I wanted to make sure that the most reduced experiments had the dominant sulfur form, the dominant oxidation state of sulfur as sulfide, capture this transition region, and then make sure that the most oxidized experiment had dominant sulfate. And I did these in Hanover at the Institute for Mineralogy in internally heated pressure vessels. And I'd be happy to go into more details if you'd like to hear those later. But importantly, the run products, these are 2 representative BSC images of run products, and all the run products contained silicate glass, which is quenched silicate melt, so that's the kind of gray background here. They all contained apatite. They were all fluid saturated, so all of them had these fluid inclusions. These are just broken open ones visible at the surface. And they all did have a spinel mineral. And important for this talk is that 8 of the experiments were sulfide saturated, evidenced by the appearance of iron sulfide melt. And 1 of them contained anhydrite and so reached the SCAS. And important also is at each of the 6 FO2 values, I had 3 different capsules in each experiment with 3 different sulfur contents. So I could see how the initial bulk sulfur content affected the sulfur behavior. So this is the same plot as what we saw earlier for viewing the Hugo model. So on the x-axis, I have the FO2 relative to FMQ, and on the y-axis is the max amount of sulfur measured in the melt. And these are my data points. So the symbols represent the run products that are present. So the circles are sulfide saturated experiments. These are the 8 sulfide saturated experiments down here. The triangle here is the 1 anhydrite saturated experiment, and the X's are all undersaturated with both sulfide and sulfate. And there are the standard errors shown for all of them. Most are smaller than the symbol size, and the error on the FO2 is plus or minus 0.25 log units. Next, I wanted to go through the literature and compare the results of my study to previous studies. And I highlight the fact that I can only add 4 data points to this plot because, as I mentioned before, most of the studies are on mafic systems. In particular, the hydrous, more evolved systems are the least studied. So these are the only studies that I could add. And I was really careful to add only those studies that are comparable to mine, because a lot of factors affect the sulfide and sulfate solubility in silicate melts. So these are really, they are comparable to my study, same temperature, pressure, composition, etc. Next, I applied the Hugo model to all of these data. And overall, it does a pretty good job. And the inputs to the model are the sulfur content at sulfide saturation. So I took the average of these points down here to define this horizontal line. And then the model takes care of the rest up here. And similarly, on the SCAS side, I took the average of these 2 points for the anhydrite saturated experiments to define this portion of the line. And here's that maximum value again. And while it does a pretty good job overall, there are 2 kind of areas where it's over predicting the sulfur content of the melt. So this model can be thought of as a sulfur saturation surface. And so any point that lies on or above it should be predicted to be saturated with sulfide or anhydrite, while any point below it should be predicted to be undersaturated. And so here we can see that these points are saturated with sulfide down here and sulfate at the intermediate FO2, but the model is predicting them to be undersaturated. So the main contribution to this paper is a kind of a new model that is based on the existing Hugo SCSS and SCAS model. And so the black line is the result of this, the new model. And what I did to do this was just tweaked the existing model parameters until the lines fit these data better. And what that really did was it kind of brought in on both sides, from both sides, the SCAS and the SCSS side, it brought that line in to be more narrow. And so what that means is that the transition from sulfide dominant to sulfate dominated melt is that this transition is occurring a lot quicker in more evolved melts than it was predicted to do so using basaltic experiments. And so here on this diagram, I have the same as what I just showed, but these gray boxes behind are kind of showing where the two models predict the kind of start to the transition, where sulfate starts to become prevalent in the melt, to where the sulfide becomes completely changed to sulfate over here. And so the lighter gray box is that region, that transition region from the original Hugo SCSS and SCAS model. And then this darker gray box is the transition region predicted from the updated model. And this is really saying that a small increase in FO2, if you have a dacitic magma sitting at about FMQ plus 1, right down here, if you just increase the FO2 by a relatively small amount, you're going to get a really large increase in the maximum amount of sulfur that melt can dissolve. And that's ultimately going to affect the mass balance of sulfur between those three components of the magma, the silicate melt, minerals, and the vapor phase. And in particular, I just want to highlight the vapor phase, the implications for that. So this is from the work of Zoltan Zajac in 2012, and this is looking at the partition coefficient of sulfur between the volatile phase and the silicate melt as a function of FO2. And here it's an NNO, but it's fairly comparable to FMQ. And what we see here is that more reduced conditions, what we'd expect based on this also is that there's more sulfur that can go into the fluid phase under reduced conditions than oxidized conditions. And so this rapid change in sulfur behavior and mobility with just a small increase in FO2 or decrease in FO2 is pretty dramatic. So that's the main conclusion from this work. Thank you. And hopefully these results will be published soon in Geochimica. And there's my contact information. So I'll take questions during the discussion session.